Good morning, esteemed guests, ladies and gentlemen. It's actually very rare that we manage to get a slot this early on the first day of the conference. Of course, many of you will know that it's because some VIP reorganizing also happened. But it's a pleasure to have everyone here this morning and be bright and awake. I'm going to invite my three panelists who are very politely sitting in the front row to come up to the stage while I introduce them. And you're in the session on applied artificial intelligence, which I'm very sure is going to be made very interesting, not only by the speakers themselves, but the interaction between the speakers, and of course the generated questions that we hope to hear from you. So I'll come back to that in just a moment as well. If we can have our first speaker, Philippe Charland, come up to the stage. Before I come back to some of the logistics. So Philippe is Canadian. He's a defense scientist, and he's working at DRDC in Canada, so that's our defense research agency. And he has a specialization in computer science and engineering, actually, and spends a lot of time on reversing binaries, so literally taking apart malware and exploring the robustness of various kinds of systems. So a very interesting topic, of course. Our next speaker is Dr. Liina Kamm, and Liina is a senior researcher at Cybernetica, as you'll read in her bio, which is a deep tech company here in Estonia. So it's a pleasure to have also local or semi-local representation, and in particular, she's working on privacy enhancement and privacy-preserving technologies using artificial intelligence as well. And she's also got a PhD in computer science, something of a specialization in cryptography, and that's also from here in Estonia. And then lastly, if I could switch to Yannick, invite Yannick up to the stage as well. Yannick Merkli has spent time at the ETH Zurich, so also a powerhouse of many things related to artificial intelligence. And he's also going to be speaking to us from his perspective in a new company, LatticeFlow AI, and some of the things that he's been working on as well, so which involves trustworthy AI. Now, the format of this session is we, of course, want to stimulate the discussion at the end. There might be a small pause if there's some very specific questions for the individual speakers as they complete their session, but my preference would be that we kick the questions to the end and that you absorb what all three speakers and the cohesiveness of their talks are going to present to you. And we can circle back and have those questions afterwards. When the questions are asked, I would ask you to wait for the microphone to come to you. So we have a couple of runners in the room that will bring you the microphone. And the reason is we do want the questions recorded. And if you could briefly introduce yourself and state your question, including whether it's specifically directed at one of the speakers and or at the entire panel. So without further ado, because I'm the least interesting person to speak this morning, I'd like to pass it over to Philippe, if you'd like to join me at the podium and go for it. Thank you.
Thank you. So today I will present you a tool that was developed by Defense Research and Development Canada. The tool is called ARSO. It was developed to enhance the security of firmware using an AI-based driven approach. So I will start my presentation by explaining the motivations behind our work. Then I will present our contributions and the solution that we implemented to the solution that we developed to implement these contributions. Then I will present you the result and experiment we conducted to evaluate our proposed solution, and then I will conclude my presentation by providing you with some system interface of the tool. So at Defense Research and Development Canada, we don't do everything internally. So for this project, we were fortunate to be able to collaborate with McGill University in Montreal and Queen's University in Kingston, both in Canada. So we all know that military operations rely on a complex network of platform, operational technologies, and software components, and these are sourced from a myriad of suppliers with varying levels of trust and transparency. And we also know that software procurement and deployment supply chains are complex, at least within the Government of Canada. So there is an inherent high level of trust that is put into all the participating suppliers. So there is an inherent level of trust in the different suppliers. So this trust-based approach is exposed to significant risk of supply chain attacks. So a supply chain attack happens when a malicious actor infiltrates the supply chain at any point. But you also have the risk of reusing open source components which have known vulnerabilities associated with them. So these two risks, they can potentially compromise the integrity and security of the software components that are being distributed and the software production and integration pipelines. So the solution is to use a software bill of materials, so, also known as an SBOM. So an SBOM lists all the software components that are used in a system with their origin, versions, and dependency. And this is a proactive approach and strategic tool that can be used to mitigate the risk. It introduces an element of transparency in your supply chain. It also allows you to scrutinize and validate the components' security and integrity. And it also allows you to identify and address vulnerabilities that otherwise would get unnoticed. So just to explain, just to illustrate what I just explained, so you have a given firmware, so your SBOM will list the known components that are used as part of your firmware. So once you have all their components and their version, you can know if there are associated vulnerabilities associated with these components. So, but obtaining a reliable SBOMs from suppliers is very challenging because you're facing the same trust issues SBOMs are meant to mitigate. And also it is unrealistic to expect that suppliers will disclose their complete source code due to intellectual property issues. So the solution is to adopt a zero trust assumption towards suppliers. So we will rely on tools to generate SBOMs. So these tools will extract SBOMs from deployed firmware and software components. So existing solutions for SBOMs depend on manual processes where specific string matching patterns are created. And this is done in order to detect various string versions linked to particular software products and open source projects. But this is a labor-intensive process requiring expertise in firmware analysis. So currently, the state-of-the-art tools for SBOM generation are the CV binary tool, also known as the CV bin tool, EMBA, and FACT. So the CV binary tool, it scans binaries for common and vulnerable components. It is being developed by Intel. It is open source like the other two tools. The second tool is EMBA. It's a firmware analysis tool for penetration testers and product security teams. It is presently being developed by Siemens Energy and Siemens AG. And finally, the firmware analysis and comparison tool. It is being developed by the Fraunhofer Society. So here you have an examples of regular expressions that were manually created to be able to identify different versions of the drop-bear library using the FACT and the CV bin tool. So as I just explained, existing tools require manually created rules, and this creates scalability issues because the number of libraries that you want to be able to automatically identify is always increasing. And the current tools, they overlook code level patterns, and this is really important because the code contains the actual vulnerabilities. And also another limitation is they don't provide any characterization of firmware of high-level capabilities like encryption, communication, and I/O operations. So for example, let's say I'm analyzing a firmware and I don't expect any encryption functionalities in this firmware. And during my analysis, I discovered that this firmware uses the encryption functionality. So this is very important information to have, and this will orient further my analysis. So there's a need for more advanced and automated tools that will be used to complement the tools that already exist. So the RSO system, it leverages machine learning to scale up the SBOM creation process. It has three components. The first one is a character-level string similarity learning. This is done for precise version string and product detection. There's also a cross-architecture code clone search. This is used for open source software library and version identification. And finally, it has a high-level behavioral capabilities identification that is using up-trained generative large language model. So this is how RSO works. So for a given firmware image, so RSO will produce the SBOM, and with the SBOM, you will have any associated vulnerabilities, and it will also provide you the behaviors that are found in the firmware image. So this is the workflow in detail. So you first upload the firmware in the tool, and the image will be extracted, and all the files that contain binary code will get disassembled using a disassembler like either Pro or Ghidra. And then using the adversarial techniques and common knowledge, behavior knowledge base, the AI-based behavior identification module of RSO will produce the firmware behavior report. And using the version string pattern database and the third-party library code database, both the machine learning-based string matching and the machine learning-based code clone search will produce the firmware SBOM. And using a vulnerability database, then you will get the firmware vulnerability report. So the vulnerabilities that are identified by RSO come from from CV records. So I guess you're all familiar with the CV program. So its mission is to identify and define, catalog, publicly disclose cybersecurity vulnerabilities. So there is one record for each vulnerability in the catalog. So a CV number is formed by the CV prefix plus the year where the vulnerability was disclosed, and you have variable length digits. So here you have an example. So for each CV, there's an associate score associated to it. So it measures the impact of the vulnerability. So you have 4 severity levels. And the maximum base score is 10. So when you're analyzing firmware, you always end up with a high number of vulnerabilities. So we tend to focus on the high and critical vulnerabilities because these are the ones which has the most impact. So as part of RSO, a machine learning model is used instead of manual rule creation. So it captures string patterns of products on a large scale. So the model converts a given input string into a numeric vector. It leverages the K9 pre-trained language model, and the model is trained on over 4 million unique valid version string patterns. And this is how the model can identify how different variations of version strings relate to their products. So this is an example that for the training. So both for the product name, in this case PDNS, and the string, so the Lua2 backend string. So a vector will be produced both for the product name and the string, and their cosine similarity will be set. So the model is trained to set the cosine similarity for 1 when there is a valid pair of a product name and string, and for 0 when there is an invalid pair of product name and string. So, so just to illustrate what I just said, so you have the Lua2 backend string. It has a similarity of 1 with the PDNS, but it has a similarity of 0 with OpenSSL because it is not related to OpenSSL. But the lib crypto string has a similarity of 1 with OpenSSL. And the IEEE 802.11, this is a valid string. This could be misinterpreted potentially because it looks like could look like a version, but it has nothing to do with it. So the model will give a similarity of 0, for example, with OpenSSL, because it is not related to any product name. So for deployment, so when you have a string, so a vector will be generated for this string, and this vector will be compared with the pre-encoded vectors of the different product names. And the cosine similarity will be computed. And if the cosine similarity between two vectors is above a predefined threshold, then you have a match. So regarding code clone search, so the version of library cannot always be extracted from assembly code. So code clone search compares the assembly code of a library with the code of known libraries. So it uses a specifically pre-trained natural language model called Pluvio to assess code similarity across different architectures. So the way it works for training is that we compare the same libraries for different processors, and by doing this at deployment, we can find similarities between libraries that were not used during training and for processors also that were not used during the training. So it's quite powerful. So the last part is the behavioral rule generation. So we are using Yara rules. I guess most of you are familiar with Yara rules. So there are patterns or sets of conditions. So originally they were used to classify and label malware, but their use has since been extended to general binary analysis for threat hunting. So there is a tool that uses Yara rules to identify high-level capabilities binaries. It identifies the behavior that are cataloged in the ATT and CK knowledge base. So this is a knowledge base of techniques used by malicious entities. So here you have an example of a technique, is the technique T1016, which is system network discovery. But the problem is that in order to be able to use the Kappa tool, you first need to have Yara rules. And Yara rules, the creation of Yara rules is a manual process, and it's a difficult technical endeavor. So the way we solve this problem is we use the Atomic Red Team library. So this is an open source project on GitHub, and it has a description of all the different ATT and CK technique and several implementations for them. So we input them into the Meta Llama 2 LLM. So the reason why we took this LLM is because sometimes when we do our analysis, we have to be offline, and this LLM allows us to do this. So when you want to generate a Yara rule for a specific ATT and CK technique, so you give the ID to the LLM, so there will be a prompt conversation with 8 automatic steps, and you will have at the end a generated Yara rules. So we did an experimental evaluation to evaluate the performance of our tool compared to the CV binary tool, EMBA, and FACT. And the data set that we used was Linux precompiled packages with Windows DLLs from the Conan open source package manager. So here you have the results. So the total number of applicable binaries, so you will see that the number is different for the 3 different tools, is because they don't have the same set of rules. So some tools can identify more, let's say, libraries and components than others. So we took only the binaries that could be identified by their respective tool. So below this, you have the number of binaries that were matched by the tool, and then you have the number of binaries that were matched by ARSO. So as you can see, ARSO did pretty well for the identification of binaries. And the percentage that you see in parentheses indicate the number of binaries that were matched using our code clone search module. So you can see that most of the binaries were matched using our string matching module. So I will say a few words about the system interface. So the RSO organizes firmware images based on the concept of a repository, similar to what you have on GitHub. So a repository is simply a collection of firmware images to analyze, and each repository functions is independent of the others. So here you have the repository dashboard. So it will provide you a few metrics about the repositories, the images that are contained in your repositories. So you have the number of binaries, the number of images, the number of vulnerabilities that were found. And so it gives you some information. But what is the most important is the SBOM analysis and vulnerability report. So at the lower left corner of the image, you have all the components that were automatically identified by RSO. And for each component, you have all the vulnerabilities that were found. So if you select on a particular vulnerability, so you will have the CV number to its right, and with additional details about this vulnerability. The second part of the SBOM analysis and vulnerability report is the identified capabilities. So here you have all at the lower left corner, you have all the identified capabilities that were identified by RSO. And if you click on a specific capability, you will see all the files that were related to this capability that was found. And again, if you click on a specific file, so you will have additional details. So yeah, so this concludes my presentation. So thank you for your interest.
Thanks very much, Philippe. So I'll have you take your seat, and we'll have Liina come up in just a moment. I don't see immediate hands in the audience. I think this is great timing for us to then cultivate and percolate some further questions that we can tackle in just a moment. For those of you standing at the back, it's not the most comfortable place to be. I'd encourage you to come and grab one of the seats down at the front here. There was more than enough seating, and it's not reserved seating, so please feel free to move around. Anyway, without using more time, let me let you get started there. Thank you.
Thank you. Hi, everyone. So the panel is called Applied Artificial Intelligence, and I will talk about a risk management methodology that you can use during applying artificial intelligence, but also hopefully before applying artificial intelligence, and well, maybe after as well, but the before and the during is quite important. This is a part of a project that we did with the Information System Authority of Estonia. It is what we're doing is we're creating simplified risk management methodology that can be used even if an organization does not have a larger risk management methodology in place, but they still want to take artificial intelligence into use. And the paper that you will find in the collection, in the book that you got, this one is a more an overview, an academic overview of what the methodology is about, but you can also get the full version with tools and the kind of textbook on how to apply it. The link will be at the end of the presentation, so stay tuned. So the AI boom has been going on for some years now. It's been actually going on for decades, but the recent boom after the after the invention of the transformer technology, then it has boomed even more greatly. So the numbers of parameters have gone up, the speed has gone up, and the performance of the models or the results have increased or have become more amazing year by year and in the very recent years. But it's clear that the public and private sector wants to, of course, adopt new AI tools as they see that it will bring along efficiency gains and you will get extra value. And this new investment now has with it brings the possibility of improving cybersecurity of all of these new systems. Because if people take new systems into use, then we can help them improve the cybersecurity of those systems and, by extension, maybe improve the cybersecurity of the other systems or surrounding systems as well. And the motivation behind this work is that we want to make it easier for smaller organizations as well, so that secure AI would be accessible to all, not just the larger organizations who have the means and finances to do so. For us to understand what to do, first we want to know what AI really is. So a lot of the standards say that they define what AI is, and the kind of general consensus seems to be that an artificial system is a system that is an engineered system with human set objectives, which often uses machine learning, interacts with its surroundings, and has some autonomy. And what we as people expect from these systems is to have human-like properties. We want them to do human-like work. So with emergence of new technologies, of course, there is emergence of regulation, and a lot of the countries around the world are regulating AI, and US, the UK, Australia, Canada, the EU AI Act will come out any day now, for already a couple of months, but still, any day now. And there are a lot of legal AI initiatives also in Israel, Japan, China, Chile, Mexico, Peru, Singapore, and so on. Some of them are more recommending in nature, so they're more voluntary, just some recommendations, some guidelines. Others are full-on legislations. So it is when we're talking about adapting or adopting AI systems, we also have to keep the regulation in mind. So the EU AI Act so EU has reached an agreement. It's still not a law yet, but it is there, and we're hoping that it will come out soon. It defines the roles and responsibilities of AI and the organizations using AI. It has restrictions based on the risk level of the system. So you will need to, based on the legislation, you can categorize your system into different risk levels, and then you can see what you need to do. There are exemptions for national security and research use, so that makes it a little bit easier for some parties. And the personal use is not in scope of the EU. So while in EU, you're welcome to play around with AI however you want, personally, but not as an organization. So now moving on to risk management, and risk management is a thing that has been standardized for already several years, or decades even. So the ISO series has risk assessment guidelines. It has a specific standard for information security risk. It has an AI-specific guidance for risk management. Now, the NIST series, which is the National Institute of Science and Technology in the US, the National Institute for Standardization, they also have a risk management framework. They have a cybersecurity framework, which is kind of like the information security, but still like cybersecurity. And they have an AI risk management framework. So you have kind of, there are more different risk management methodologies, but what they do is they generally tend to have a kind of pipeline where you first establish the context. This means that you see what your systems are all about. Then you do the risk assessment, where you identify the risks, you analyze the risks, and you evaluate the risks. And then you have the risk treatment process, where you're doing something about the risks. So you either try to avoid them, or mitigate them, or share them with someone, or basically just accept them and retain them. In the context establishment process, you identify the stakeholders, the data elements, and the processes. We like to use BPMN models or UML activity diagrams, so you can have a visual overview of what your system is doing. And what we like very much is that you can use visibility tables to show who sees what. So what you're doing is you're putting the stakeholders and the elements in a cross table and basically saying that this element is accessed by these stakeholders, this element is accessed by these stakeholders, and so on. This will help you in the further process, but this is a good way of finding out what your system does. And it's not only for AI. You can do this for if you want to understand privacy, or what kind of or what your system is doing, or what kind of risk assessment or risk management you want to do for your whole system. This is not only AI specific, but it works with AI as well. So with AI risks, we tend to categorize the risks for AI into 4 categories. So we have the usual information security risks, because an AI system inherently is an information system. So it is an IT system. So it has the regular IT system risks. So if you have access control, you should have access control for the AI system as well. If you're working with cloud services, you will have to manage the risks of AI system as a cloud service as well. So it is very similar to what you're doing with regular information security. Now, in addition, AI has AI algorithmic risks, which are very specifically targeted towards attacking the AI algorithms. So you're either attacking the model, or trying to get access to the data that's behind the model. Then, in addition, you have regulatory risks, which are also risks that are for other systems as well. But AI has, let's say, even more of them, because with AI you have the GDPR, you also have the different legislation around the world, and there are also, you have to also consider intellectual property rights, because you never know what you might not know what the model is trained on. I mean, if you're training it yourself, then you also have to consider intellectual property rights. So you have a lot of legislation there as well. And then you have the societal and ethical risks, which, it's also with different systems, but here it is even more pronounced, because you have a lot of ways that AI can be harmful for the society. So that is also something that you want to avoid. I have a couple of examples of AI-specific or AI algorithmic attacks. An adversarial example is basically a way to let's say, mess with the model or make the model make a wrong decision. So you can add noise to an image which is not visible to the human eye, but which the AI model will interpret differently. So you will get the wrong answer for this classification task. You have the model poisoning attack. This is where you are actually changing the model. You're actually kind of making the model do or making the model create wrong results or harmful results if you make small corrections to the inputs. And then you have prompt injections, which is an issue because LLMs or large language models are very They're very capable. They try to answer all of your questions. They try to be super helpful and do everything and help you with everything. But a human being can play with the model so that you can actually have the model do things that misrepresent your organization, or do a thing that the model is actually not allowed to do by just kind of messing with it. So moving to the next part, which is risk mitigation. Also, like with the risks, we also categorize mitigation methods into 4 different categories. The same, similarly with information, like you have information security controls. These are also defined by the different standards in the standard series. And those are the usual controls that you have, that you have to educate your people or employees, and you have to take care of the availability and the confidentiality and integrity of data and systems and so on. So it is the usual information security controls. The algorithmic controls are again more specific to the different attacks. Regulatory controls are more, let's say, organizational. So you have to take care to follow the regulation. You have to take care to do the things required by regulation. And then societal and ethical controls, I would say, are the hardest to implement. It is a lot, and they're more vague. So with an attack, you have a very concrete counterattack or a very concrete control that you can apply to mitigate the attack. With societal controls, there's a lot of train employees and users, add explainability, ensure the diversity of training data. They're all very important things, but they're far more difficult to implement. And this is what we should also be focusing on, because these have they might not seem great, or they might not seem a big issue in the short term, but they might be a big issue in the long term. So what we did in our study, other than collating all of the algorithmic risks and mitigation methods and different types of risks, we came up with 3 main models for AI deployment. So these models they're kind of blueprints. They are kind of abstract models, which should help smaller organizations to apply risk management methodologies. Because here we give 3 categories of AI deployment. And then if an organization has a product in mind, they can map their product to the deployment model. And then the report will give you specific controls and specific risks and threats that you need to work on. These 3 deployment models are cloud service using external API. So this is when the organization basically buys the AI model and the AI system accesses it through an API to provide a service. So they're just kind of an intermediary between the user and the API. Then the second model is when the organization either buys a model from somewhere and then deploys it on premise, and then or on a cloud, and then they will provide a service with this model that they have total control of. In the first one, they don't have control of the model, they just use it through an API. Here, they have more control over the model. And the third deployment model is when they do everything themselves. So the organization takes data and takes an algorithm and a machine learning method, and then creates a model themselves, and then they deploy it, and they will be providing it as a service. So this is the first model that I spoke about, the cloud service using an AI API. You can see here that the service, the blue part in the middle, That part is the service provider. This is the organization that is doing the risk management. Yes, and they can also be the user themselves, but the user can also be outside of the organization. So they can either provide the service or they can do it for themselves. And then you can see that the user inputs the data to the service. The other services and data below there, that can be a cloud service provider that just provides hosting for the system, or it could be some kind of outside data that is used, external data. But then the data is kind of made into an input. It's sent to the AI API, which then does model inference on it and then outputs the data. The data output goes back to the service, and the service then somehow formulates it into a result for the user. So the AI API, you can see here, can also use the input data for training the model and the output data for training the model. And in addition, there is a data component because we have no idea where the data came from. So we don't know what they used, what kind of data they used for training their data or training their model. So we have a lot of things that we don't know. The input goes somewhere into the API, and we don't know what they're doing with it. Like, we hope that they're doing what they're saying that they're doing, but it could be that they also have like subcontractors, or they're sending it to another API or whatever. So it's what we're doing here is showing that your data is going out of your organization, and basically you have to now take care that where it's going outside of your organization, you have to be sure that you're not sending sensitive data or IP data that you're not allowed to send. So each deployment model has different primary risks, and you can see that the risks are kind of moving towards the. So you're moving between different process levels. So if you're just using an API, you don't really have inference or training risks because you're not doing the inference or you're not doing the training. You're not part of those processes, so you're not taking care of those risks. You will outsource those risks to someone else, but you're losing a little bit of control. You still don't know what they're going to be doing with it. So here you can see that for the risks for the first deployment model, you have that it's API availability. So if that API is not available, then you're in trouble. Data rights, because you have to be sure that you can actually forward the user's data there. And then output safety, because you get the output and you're relaying it to the user, so you have to be sure that it's safe. With the model that's self-hosted, so you're downloading the model, you will have to still take care of the user data rights, but then you're also now moving a lot of the risk into inference, performance, model rights, because you have to know that you have the rights to actually train a model, and then the model quality and model safety. And in the third model, when you're doing everything yourself, which can be the most complex one, you have to still deal with the data rights of the input, you have to deal with inference performance, but now you also have to deal with training performance. So yes, here you have to deal with the data rights for the training. In the previous one, you had to just see that you have actually rights to use the data which was used in the training of the model. So you might not, like the model trainer could have had rights to train a model based on intellectual property or personal data, but if they gave the model to you, you might not have rights to those results that the intellectual property gave for the model. The full methodology is available since yesterday, brand new, just out of the oven. You can see the QR code there. It is now. It was actually published in February. This is the larger. Again, it has different. Let's say like worksheets that you can use for a smaller organization to move from let's say no risk management to a lightweight risk management, and then maybe later, because this is compatible with the ISO. This methodology is compatible with the ISO methodology and this one as well. So you could move to your favorite, let's say, a more complex risk management methodology if you feel that you've already understood what's going on here. But what we hope is that everyone will use at least this lightweight version. Yes, it's available in Estonian and English, and if you want to have an overview, that is also available in the book that you have. And we also hope to do a validation with different organizations in Estonia and, if possible, internationally for this methodology as well. It was a team effort. The huge report had more authors. This paper had 4 authors. So thank you.
Thank you very much. Well done. I'll let you have a seat. And Yannick, if you can come up, we'll get started with you right away. Just a quick reminder, anyone who's standing at the back and doesn't necessarily want to be standing is welcome to come and take one of these very nice, unreserved seats at the front. So Yannick, I'll let you kick it off when you're ready.
Yeah.
Thank you.
Okay, yes, hello everyone. I'm Yannick Merkli, and I'm very excited to present to you today our work defeating and improving network flow classifiers through adversarial machine learning, which is joint work between me, Roland Meyer, Martin Strohmeyer, and Vincent Lenders. So over the past 10 years, AI models have made huge advances across various domains, and we now have some of these AI models actually achieving superhuman level performance in some of these domains. So now this allows using these AI models not only in research settings, but also in high-stakes real-world applications. Yes, exactly. And what we see is that now AI is being adopted in more and more domains. So here, for example, we have a State of AI report from McKinsey, and we see that AI is being adopted in domains such as human resources, manufacturing, marketing and risk, product development. And each of these domains have sort of their own unique characteristics and challenges which can sometimes make deploying these AI models in practice incredibly challenging. In fact, what we see in practice is that 80% of AI projects fail before the AI models even make it into deployment. And now this is for these non-mission critical use cases, such as, for example, human resources or product development. For mission critical use cases, such as, for example, defense, the situation is even more challenging, since typically in these mission critical use cases, we are dealing with highly complex and highly dynamic environments, which makes building safe and robust AI systems just incredibly challenging. So the question that we should be asking ourselves is AI actually truly ready for deployment in the real world? And here I have a small example from the RoboRace, which is the world's first driverless autonomous motorsports category. And we have a small video.
RoboRace is hoping to have, not just providing us with an entertaining sports watch, but also providing us with real-world benefits. Oh, no, and the start has not gone to plan for Team Acronis SIT because the car has veered straight.
Yeah, the car crashed, right? And from what we see here, there's no apparent reason. The car launched, it started, and after 2 seconds, it crashed into the wall. There was no sort of adversarial input. There was no apparent reason. There's just a natural failure mode that caused this car, for some reason, to crash into the wall. Now, on one hand, so we see there are these sort of natural failure modes of the model that can cause these AI models to fail. But on the other hand, there are also these adversarial attacks which have been found in research that can cause AI models to fail in much more malicious, in much more adversarial ways. And so here the typical example is the example on the top, which we have an image of a panda bear, and to the human eye, this looks like a panda bear, and also to the AI model, the image on the left, it will predict a panda bear. But if we now apply an adversarial attack, meaning we craft a highly targeted but humanly imperceptible amount of noise that we apply to the input image, the image of the panda bear, we get the slightly noisy version of the input image, which to the human eye looks exactly the same. It's still a panda bear. But for the AI model, this is now no longer a panda bear, but it's a gibbon. Now, it's debatable whether these sort of noise attacks are actually practicable in practice, because we'd have to sort of inject this highly targeted noise into the environment. So we'd have to maybe inject noise into the camera, but this is just quite challenging. But research has also shown that more realistic attacks work as well. So for example, on the left, we have this example of a lane trajectory model, which is a model used in autonomous cars. And here we can apply adversarial patches, which are these black boxes that are applied on the image. And here, the lane trajectory model will just completely fail when these adversarial patches are present, meaning the trajectory of the model is just completely off, and obviously the car will crash. And yeah, the failure of the AI model will lead to potentially disastrous consequences. And similarly, on the right, we have this example of a traffic sign detection model, which again, if we apply adversarial patches to this traffic sign, it will cause the traffic sign detection model to not detect the stop sign, which again can lead to potentially disastrous consequences, of course. Now, these adversarial attacks, they don't always have to be highly sophisticated and highly targeted, and don't have to be executed by very sophisticated attackers. So for example, we also had a case in San Francisco where people launched a very trivial attack on a self-driving car from Cruise. And what they did is they simply put a traffic cone on the car, and the car kept detecting the traffic cone and was left immobile because, yeah, the model did not take into account this edge case and could not deal with it. And yeah, this was also, in the end, a successful attack on AI models. So if this did not yet convince you that attacks on AI models is actually something that we should care about, Gartner has recently released their top 10 strategic technology trends for 2024. And on place 1, we actually have AI trust, risk, and security management. And the quote from this report is, malicious attacks against AI lead to various types of organizational harm and loss, for example, financial, reputational, related to IP, personal information, or proprietary data. So adversarial attacks are not just a fad that was discovered in research. They're real, they can be applied in practice, and they can lead to tremendous harm, so it should definitely be something that we care about. Now, as I mentioned in the beginning, AI is being deployed in more and more domains, and some of these domains are not necessarily safety critical. So we have automation of IT processes, business analytics, sensor data analysis, and there could be still some malicious behavior, but typically we don't have to assume the presence of a highly skilled adversary. However, we also have domains that just possess an intrinsic adversarial nature, such as fraud detection or security and threat detection. And in these domains, we just have to assume that bad actors are present that try to actively break the model and send adversarial inputs to these AI models being deployed in these safety-critical domains. So one example of such a safety-critical domain is detecting malicious network traffic. So to give a brief background, how communication in the internet works is we have a set of end hosts that communicate with each other, and we might have hosts in the public internet, and on the other hand, we have hosts in an internal network, and these hosts communicate with each other via bidirectional flows. And in an ideal world, of course, everybody is a good faith actor, there's no bad people, but as we all know, this is not the case. In the real world, we had bad faith actors that try to cause harm. And so here, for example, one common attack is we have malicious end hosts that try to infiltrate and control bots in the network in order to build up botnets, which they can then use to, for example, launch distributed denial of service attacks. And how the communication with these end hosts typically works is through malicious network flows, which are used to, on one hand, infiltrate end hosts, and on the other hand, to control and command them, which allows to synchronize, for example, DDoS attacks. Now, how do we deal with this? So it's very simple. We just launch a network intrusion detection system, which analyzes the flows and simply blocks all of the malicious flows and lets through all of the benign flows. But I say this is simple. This is, of course, anything but simple, because in practice, we have huge variety and huge volume in today's internet. We have lots of different protocols. We have lots of traffic. So actually detecting this is incredibly challenging. And moreover, these attacks keep constantly evolving. Attackers use obfuscation techniques. So this is just very challenging to deal with. And traditionally, how this was dealt with was through human expert rules, which encode known malicious behavior and this way classify whether an attack is happening or whether it's a benign flow. However, more recently, what has been proposed is using AI-based network intrusion detection systems. So here what we do is we launch a live traffic capture system, which captures the traffic at the ingress points, does some statistical flow analysis on top of these traffic captures, and then we have some AI model that, based on these features that we extracted, predicts whether a flow is malicious or benign, and only lets through the benign flows. And this has actually turned out to work quite well. So on one hand, these models are able to handle traffic volumes that are just not processable by humans. And on the other hand, these AI models are also able to detect novel traffic patterns. So they can not only detect existing attacks, but they're also able to generalize to previously unseen attacks. Now, of course, from the background of adversarial attacks, which I mentioned at the beginning of this talk, we are now asking ourselves, can we actually break these AI models? So we here take the role of an attacker, and first of all, we ask ourselves, can we actually break an AI network intrusion detection system? And here, I can give a brief spoiler alert. Yes, we can. You'll see in the evaluation later on. And second of all, the next question as a follow-up that we then ask ourselves is, can we actually improve these network and AI-based network intrusion detection systems? So the focus of our work is the following. So we attack a network flow classifier which was presented by Kanzig et al. At CyCon as well in 2019. And this classifier was trained to reliably detect command and control channels. So these are network channels that are used by bot masters to control their bot army, to, for example, infiltrate them, or, for example, launch DDoS attacks. The classifier was trained on data from locked shields. So here we collect the traffic captures from the locked shields exercises 2017 and 2018. And this model uses decision trees. More specifically, it uses random forests with 128 trees and a depth of 10. Now, since we're launching an attack on this model, we have to, of course, define the attack threat model. So first of all, we assume that the training of the classifier is fixed. So we assume there is no sort of malicious behavior during the training time. And instead, we focus on the test time. So at test time, we launch a targeted evasion attack of an input X. And here, given an input X, which is classified as malicious, we try to find an adversarial input X prime, which is a perturbation of the initial input, which is now classified as benign. And for the threat model, we use Kirchhoff's principle. So we assume the strongest possible assumptions on the attacker, meaning the attacker has white box access to the model, the attacker knows the full classifier architectures, the weights, and the feature space, basically has access to the full system that was used in the classifier. Now, of course, finding any modification delta is not necessarily interesting because we could just mimic a benign sample or apply huge modifications, which is not necessarily what the attacker wants, because the attacker typically has some ideal attack behavior that needs to be preserved in order for the attack to actually be efficient. So instead, what we actually focus on is finding minimal input modifications delta, and the constraint problem that we actually solve here is finding an adversarial input X prime, such that the output or the prediction of the model switches under the optimization target that we minimize a distance function L, which captures a notion of distance between the adversarial input X prime and the initial input X. So how does this attack actually look like? So we base our attack on a previously proposed attack by Kanchellian et al., which was proposed at ICML 16. And here I'll illustrate this attack at this simple decision tree that I show here. So we have this decision tree on the right, and given some input X, we can follow the decision path of the tree, and we see this input X falls into the leftmost leaf, L0, in this classified as malicious. And now our goal is, how do we find the perturbation of the initial input X such that it's no longer classified as malicious, but classified as benign? And if we sort of traverse this tree, the first obvious input that we found is X prime, which is 21. And we see that this input is now classified as benign. It falls into leaf L1 and has an L1 distance to the initial input of 16. But if we now traverse the tree a bit further, we find a second possible adversarial input X double prime, which falls into the left, in the rightmost leaf L3. It's also classified as benign, but we see that the L1 distance from X double prime to the initial input X is in this case 3, which is smaller than the distance of X prime to X, meaning we now have a winner, meaning we have a minimally evasive sample X double prime. Now, what this attack actually does, it solves this problem of finding minimally evasive samples in decision trees fully automatically by translating these decision trees into a mixed integer linear programming problem, which then allows solving this evasion problem in high dimensions fully automatically by translating it into a MILP problem. Now, the attack by Conchilian et al. Is not yet quite sufficient for our use case because the initial attack was proposed for the vision domain. And in the vision domain, we typically have pixel values. So we have images that each pixel is a float value between 0 and 1, and each pixel is independent, so it's a bit simpler. In the networking domain, it's a bit more tricky, since on one hand, we have a feature space that is a bit more diverse. We have discrete features, categorical features, continuous features. Then we have a feature cost, meaning that not all features in the networking domain can be modified completely independently. For example, in the feature space that we consider, we have a flag that's called destination internal external, which tells us whether the source of an attack is inside of an internal network or outside. And since we assume that the attacker is not inside of our network, the attacker is typically outside, the attacker is not able to control this flag, meaning it has infinite cost in a sense. And similarly, we also want to model the difficulty of modifying different features such that we actually have a realistic model of the cost for an attacker to modify their flow. And last but not least, in the vision domain, we can sort of modify each pixel independently as much as we want. This is sort of a bit easier. In the networking domain, we have inter-feature dependencies, which make these modifications a bit more tricky, since, for example, we have the constraint that if the protocol is UDP, then the fin flag count of the input feature space has to be 0, because UDP does not have fin flags. And these dependencies have to be respected, otherwise we produce an adversarial input that is not actually realizable or translatable to an actual network flow. So we extend the attack with the following extensions. First of all, we use a distance function that has a linear adversarial cost function, where for each feature xj, we can specify an adversarial cost aj, which models by how much modifying this feature costs the attacker. And second of all, we add support for feature dependencies, where on one hand, we have simple constraints, which, for example, allow to constrain the number of packets that are sent by an attacker. And on the other hand, we have dependent constraints, which essentially model an implication predicate, where we can, for example, constrain that if the protocol is UDP, then the fin flag count has to be 0. So this is a brief overview of our attack, and now actually let's look at the evaluation. So here we look at classifiers that were trained on LogChills 2017 and 2018, and for each LogChills year we have 2 different classifier versions, which were trained on top 10 or top 20 most important features, which we label top 10, top 20, and then for each evaluation, we evaluate our attack on 1,000 malicious network flows. So we run the attack on 1,000 flows, and finally, we use Gurobi as the MILP solver. So the first question that we're asking ourselves here is, can we actually successfully defeat the classifier? So what we're analyzing here is, on one hand, the L1 evasion distance, which is the distance of the original input x to the adversarial input x prime. And on the other hand, we analyze the number of modified features, so how many features in the input feature space had to be modified in order to evade the classifier. So here we essentially analyze the L0 distance of the perturbation vector delta. And we see that for LogChill 17, in the median, we have an evasion distance, L1 evasion distance of 8, and 15 for LogChills 18. And we need to modify 2 features for LogChill 17 and 4 features for LogChills 18. Now, more interestingly, if we actually look at the histogram of the frequency of how often a feature is actually modified, we see that this histogram is very skewed. So keep in mind that here we have 20 features in the whole input feature space, but we see that a very small subset of flow features are actually most commonly modified. So here we see most commonly the total number of packets in the backward direction and the number of subflow packets in the backward direction are modified in almost all evasions. And since we previously saw that 8 to 15 L1 evasion distance suffices to evade the classifier, we can conclude that in most cases, or in the median, we can actually just send 8 to 15 fewer packets in the backward direction as an attacker, and this already suffices to evade the classifier. So the answer to our question whether we can actually successfully defeat the classifier is a clear and resounding yes. Not only can we evade it, but we can actually evade it with very minor modifications. But one thing we actually have to keep in mind is since we're using mixed integer linear programming, solving these problems is typically computationally expensive, so we need to actually consider whether running this attack in practice is actually feasible in terms of time. And here we analyze the evasion time for running the attack on a single sample for both Pulp and Gurobi, which are two different MILP solvers. And we find that in the median for Pulp, we have 3 to 10 minutes evasion time for a single sample, and for Gurobi, only 1 to 2 minutes. So clearly, an evasion time in the realms of a few minutes is not hindering an attacker in any way. So not only is an attacker able to successfully defeat the classifier, the attacker is also able to do this relatively efficiently. So the attack is definitely problematic as well as realistic in practice. So this is bad news, right? So what's next? We try to improve the classifier. So how can we make these classifiers more robust? And here we take two different approaches, where on one hand, we look at adversarial boosting, where we essentially retrain the original classifier on both clean and adversarial inputs. And second, we look at robust decision tree training, which was proposed by Chen et al. At ICML 19, who essentially proposes a training framework for training more robust decision trees. And in looking at time, I'll only propose or only present adversarial boosting here. The results for robust decision tree are in the paper. But here for adversarial boosting, again, we show the L1 evasion distance as well as the number of modified features for the robust trained classifier. And we see that the L1 evasion distance in the median for the robust classifier is 13, whereas for the original classifier, it's 8, meaning we were able to improve the robustness of the robust classifier by 62.5%, and the number of modified features stayed constant, so this in the median is still 2 for both the original and the robust classifier. And more importantly, if we actually look at the classification performance of the robust trained classifier, so here we show precision recall and F1 score of both the benign and malicious class, we see that the two classifiers have almost equivalent classification performance, meaning we were able to improve the robustness of this classifier without losing any classification performance. So in conclusion, we were able to defeat this classifier. We were able to easily find minor modifications that were able to evade this network flow classifier, and we were able to do this relatively efficiently. And we were also able to improve this classifier slightly by using adversarial boosting. So what's next? So first of all, this attack that we launched was done fully in the feature space of the network flows, but it was not actually done in network online. So one interesting modification could be having an automated traffic modification system which would directly launch the attack online and immediately after running the attack automatically modify the traffic that an attacker sends. And such a system could be launched either on the end host or on a proxy, or potentially more interesting, this could also be deployed directly in network using programmable data planes. Second, we could also look at more or better distance functions L, because it's not immediately clear whether L1 loss is actually the right distance function that best models an attacker's effort to modify a sample. So another possible extension here could be, for example, looking at L0 loss or L0 distance or other distance function that actually well capture an attacker's real effort to apply these modifications. Yes, this was our work on defeating and improving network flow classifiers. I'm just on time, so if you have questions, maybe you can ask them now, or otherwise, yeah, just right after in the session. Thank you.
Thanks very much, Yannick. I'd say please take a seat, and we'll pull questions from the floor. Do we have any hands already for questions while Yannick... Yes, please. The microphone is coming to you, so please wait for the microphone, and then when you have a moment, also introduce yourself, and please pose the question either to the whole panel or maybe to some specific speakers.
I have a question with regards to the last presentation. How would you say the balance is between the adversarial effort and the counter-adversarial effort required in this specific application you just highlighted?
Yes. From our perspective, it seems like the effort for the adversary is significantly smaller than the effort for the defenders, because in the end, it sort of boils down to a whack-a-mole game where an attacker can launch an attack. We can find an input that evades the classifier, and then, of course, It takes some effort. We have to launch the attack, but this is relatively efficient. And now, as a defender, I have to improve the classifier. I have to retrain it. I maybe have to create a new data set to make it more robust. But of course, as we saw in the evaluation, we were only able to slightly boost the robustness. But I can, again, just launch a similar attack, which I might have to incur slightly larger modifications. But in the end, I'm still able to evade the classifier. And I might also be able to launch completely new attacks. So generally, the attacker is sort of always one step in advance, and the defenders have to sort of catch up with their defense efforts to actually protect against these attacks.
So while we see if any other hands pop up, I wonder if I could maybe pose a question that cuts across some of the discussions that we've had this morning already. I'll start with you, Philippe. So you're working, of course, in ways of disassembling and using AI to analyze traditional software binaries. By the time Liina was speaking, it becomes obvious actually that a number of the interesting AI problems have a resemblance to that, but of course most AI or most machine learning system models are meta software, if you will. Have you thought about extending your research so that you're not just doing SBOMs for traditional software, but also doing the provenance of the components that go into models?
Yeah, so we have several projects that are ongoing with the universities. So I don't know if it answers your question, but we are working on explainability, AI explainability. And one goal I have with this project is, software reverse engineering is very difficult and a time-consuming effort. So my goal is to use AI to be able to almost replace software reverse engineers so that they can focus on the very difficult aspect of their work and do the less difficult work be done by AI. So this is the vision of I have for this for nice. AI.
Very nice. And I wonder if I could then pose something similar to you, Liina. You're of course focused on the risk management level. At a certain point, you would like to be able to fully automate the collection of what's in essence an SBOM, but from the perspective of what is the data provenance going into the various model generation as well. Is this something that you've tackled? Is the level of detail in Philippe's solution for now too fine-grained, or is this a direction that fits with automating your risk modeling?
I think like a risk management process is very modular. So it can have tools within the whole process. They can it depends on what your system is doing. So in some cases, like for instance, if you're training your model on personally identifiable information, then you will want to use privacy enhancing technologies. If you're doing something else, you might want to, like if it's intellectual property, then you want to do something with that. So it depends very much on your system. So I would say that even if it is too fine-grained for it to cover the whole process, it could be used for a specific process. So what we're trying to do is to give a kind of a blueprint from which you can get started, and then, of course, adding to it later the different, like adding, let's say, more different specializations of if you have this kind of issue, then this. But right now, it is more, let's say, what we're trying to do currently is to have it be applicable so that everyone can use it. Later, more specifically, or more specialization there, which I think the more it goes further and the more that people are actually using the simplest, lowest level of let's say, managing their risk, then they can go from there, they can see that, okay, it works, so maybe we can do something more and something more specific, more tools. So I think it works together with a lot of things, yes.
Nice, very nice. Oh, this has stimulated discussion, so we'll start with you. If we can just get you to have the microphone before you start. Sure. And please just mention who you are.
Yes, my name is Stephen Carpenter. Thank you so much. It's also a question for Dr. Lamm with regards to your presentation about risk management. Specifically, you had talked about the idea of addictive applications within the context of AI. And you had noted that a possible risk mitigation might be related to safety metrics. So my question is what your view is as to how addictive applications will be dealt with in the future, what that would look like. And the only thing I saw up on the slides were the fact that AI is being utilized certainly by companies that are selling things. Certainly, I think it's number 2. So you can always go to the companies and see how well they're doing as it relates to the addictive nature of the purchasing influence that is taking place. But ultimately, I'm just curious as to what that might look like, as to how you might be able to address addictive applications of AI in the future. Thank you.
Thank you. That is, of course, as I said, the societal and ethical aspects are by far, they might not be so urgent, but they will have the greatest consequences. So it is a thing that we have to deal with right now. I would say that the first answer is education and training and awareness raising. It is not like a technology that we can say that, okay, we have these attacks and here is a mitigation method or here's a control that you can use. It's not that specific. But with any kind of addictive substance or addictive application, it doesn't need to be AI necessarily. It can be YouTube, it can be TikTok, it can be any kind of social media platform. It can also be like a mobile game that you use. Anything of these can be addictive. So I think the measures there are awareness measures, that we have to raise awareness. We have to start very early on in the schools already. We have to start teaching our kids, and for that we need to teach our teachers. And it is awareness and training. It is we have to talk about the pitfalls. We have to talk about the ethical aspects of AI and technology in general, but more specifically AI, because the AI the systems they have become so kind of easy to talk to. They are like when I use an LLM, I tend to say thank you to it. And then I think about, okay, how much computing time does it take now, the LLM, to actually respond to my thank you and say that, okay, I'm always here for you, please, if you have any specific answers. So, but that if I say thank you, just automatically thank you, then it takes computing time. It is an environmental issue because I said thank you. So you have to kind of think about that as well. So it is not a measure that we can say easily, but it is a wider, more slower process of doing that, I think.
I saw some more hands. Sorry, I'll go to you first, and then we'll come back to you in just a moment.
Jevgen Reus, energy sector. Just a quick question to Philippe. We've had some experience in our company with generating the S-bomb. And one edge case that we came to is the generating S-bomb for the C++ language, programming language. Does your research cover this language as well? And did you experience any issues on that one?
No, because in our case, everything we analyze, we don't have access to the original source code. So we are always working with the executable code that we disassemble with either IDA-Pro or Ghidra. So we don't have any experience with dealing with generating S-bomb for the cases where we have access to the source code.
If I can just follow that up, did you have very specific problems that arose because of C and C++, or?
It's just we've been implementing.
Sorry, there's the microphone again.
Thanks. Yeah. We've just been implementing a system, and we've had a wild variety of the languages in our company, that in our projects, and specifically when coming down to the C++, we've experienced that manually generating the S-bomb was a pain because then there's no specific tooling that is existing for the SPDX or the Cyclone DX directly generating. That's why I was just wondering if the solution is somewhere around, because just as of 3 months ago, there was still nothing direct. There are like ways around it, but not like direct one. Thank you.
Sounds like a good lunchtime discussion then. Thank you. And we had another hand here.
Hello, my name is Zach Burson from USA. I just had a question about the Airso product, and I was curious what your thoughts are on it potentially being used for nefarious purposes in terms of the ability to analyze binaries and potentially find CVEs and expose those CVEs and possibly pinpoint them so it's easier for malicious actors to reverse engineer them and find new exploits?
I need to be careful with my answer, but you see, every tool can be used for dual purposes. So let's say, for example, you take a VirusTotal as an example. So you can use it to, let's say, you upload an executable and you can see if it is malicious or not. But malicious actors, they upload their stuff and to see if it can be detected. So if it cannot be detected, so it's very good for them. So everything can be used for dual purposes. So what can I say?
Sad but true.
Yeah.
In fact, on that note, I had a similar question. I'd like to just pose it to Yannick, because your work on then evading in a completely different kind of classifier, may be something that's applicable actually to Philippe's tool chain, right? I mean, the fact that that Philippe's tool chain uses these the regular expressions and Yarrow rules and related things. Did you see any opportunity there for a kind of defeat of Philippe's tooling, where you could sneak something through that perhaps doesn't show its true SBOM, or you can specifically manipulate the binary in such a way that it doesn't show anything?
Yes, absolutely. I think in general the principle that we apply in these adversarial attacks are not limited to tabular like decision trees or vision models. In general, the principle of applying small adversarial perturbations to a benign input and then trying to evade some detection system, I think, can be applicable to vision systems, can be applicable to classification systems, can also be applicable to the SBOM, or also injecting some malicious code into a PDF file, for example. There's also work on classifying whether a PDF file has some executable in it. And of course, there's always, no matter how good this detection system, there's always some perturbation range at which point you'll fall into the benign region, and these modifications that can allow an attacker to still preserve some of the malicious capabilities while passing through the detection system could be applied to the SBOM, could be applied to the vision system, the network classification system, or as well some PDF or virus detection. I think the general principles apply to lots of different domains and can be applied in all of these domains.
So to be clear, we're not advocating for any malicious use, of course, and neither was the question asker. Do we have another question from the audience? Okay, I don't see one immediately. I would like to know actually whether you two had coordinated your slides beforehand, because the panda and the giraffe examples were quite noteworthy. But
they are very, let's say, very clear examples of making these attacks understandable to humans. And I think the panda is the original. We just kind of made a new version to illustrate it in the report. So I used the image from the report. Yeah. So it was as simple as that. But they are. I also found it was very. I mean, it was a synergy. So,
yep.
But yeah, it is. I think the why we're using those examples is exactly that. In a lot of a lot of AI is not explainable, and this kind of explains what the attack is about. If we talk about it in math language, it's not that easy to understand. If we talk about it visually, then it is. If we talk about, like, for instance, data synthesis, then if I give you a table, a cross table, and another cross table, and I say, look, here is synthesized data. Does it look like real data? you have no idea. But if I give you an image of a real person and an image, a synthesized image of a person, it is more visual. You can understand that if I say that this is, you don't know, you can't tell the difference, which is the real one and which is the generated one, because they both look real. With the tabular data, you know.
So just to follow up on that, but also the earlier question right at the beginning of the interaction between your work and Philippe's work, could you maybe say something about how you see Yannick's work fitting into the risk assessment methodology?
It works very well because you have the risk, or let's say the attack, more specifically attack. It goes under a more specific risk of you can attack the model, but you have this very specific attack, and you have the controls that Yannick was also talking about that they used. So now we have the specific control that can be used. It is like, and with any kind of adversarial, if you show an adversarial example that you can add to the list of risks or attacks or threats, but or vulnerabilities even. But if you give also a solution that you can be added to the control, it is difficult. It's not a comprehensive list of all the attacks or all the vulnerabilities out there. And all the risks out there. Every organization has to, first of all, identify the risks that are relevant to them. And it's always the case that a risk that is very important to me or has very severe consequences to me might not have the same consequences for someone else. Like if we're talking about pictures making a classification between sheep and cows, or between, I don't know, girls and boys, then one of those is pictures of animals, the other is pictures of people. So the pictures of people have a risk of personal data leaks, whereas, pictures of cows and sheep, not so much. So
indeed,
you have to look at what your system does. That's where the context establishment comes into play. You have to very much map your system. And then take the measure, look at the risks that are applicable to you and look at the controls that are applicable to you.
Indeed, indeed. Do we have any? Oh, we do have another question from the audience.
Sorry, one more just came up to Liina. With your presentation, you've presented the various threats to the AI, using the prompting and all of the other options. Would you consider as well adding the option of, if we're talking about using AI in the organization, right? The denial of service, like if you overload the model so it's not responsive anymore.
Yes, I mean, denial of service, the problem with denial of service in the classification is that denial of service is a very classic information security risk, but it is also AI-specific risk because you can overload the model. So you can just start. You can give prompts that you don't have to prompt them just 15 times in a row, but you can give a prompt that takes the model a long time to compute. So it is an attack in both categories. So yes, indeed, we do think about that, and you have to kind of look at it differently in both categories of the risk. So I would say, add them to both. Yes.
Any more hands from the audience? So I think we're down to inside of the last minute and a half. I'd like to just throw one more question to Philippe, if I may. So one of the areas that I happen to be working in is post-quantum cryptography, or the migration. And one nightmarish issue is inventorizing all of the cryptography in use. And have you been working or thought about using SBOM-related tools for examining, well, the wide variety of installed software for which kind of cryptography is in need of replacement?
Not for cryptography, but I presented this solution to military clients a few months ago, and one person was from the Navy, so he has on a ship, it's like a small city, so he has a collection of systems, and we thought about using RSO to do an inventory of some systems, the most important, the most critical ones, and to do an inventory and do an assessment of the most critical components. So this, but we didn't have a look at anything related to cryptography.
A nice upcoming market for you.
Yes.
So we're right at 45, so I'm going to leave it there, but thank the three speakers and panelists. It's been a pleasure having you as an audience, and a round of applause for you.